to Oscar. Oscar, what do you got? Any news or any
No,
questions?
I'm myself. Good afternoon, everyone. I'm really ashamed I didn't change my calendar for the daylight saving time. So I say I'm coming in early, and it happens to be that I'm 1 hour late. So I
Sorry.
apologize for that. It will not happen again. It's
Oh,
already fixed.
yeah.
But about the problem that you're saying, it is quite interesting. We are working with the machine learning data analysis, identifying the k-mean clustering and several analyses. Actually, right now I'm working on the software flowchart of what we're doing in real time, and we are added to it a. And I missed your presentation, which I think that's before I open my mouth. Should have heard. I think you need like neural processing unit to do that and analyze the data. So instead of having your CPU doing that, the machine learning analysis, it should be done the analysis by these type of neural processes units that they work about 26 tera operations per second. And and by the way, the power is about 2 watts. Now you want it for April. This is quite challenging. Uh, we are we are actually working on similar system, taking magnetic data and 3D vectors and analyzing them and looking for anomalies and correlations and so on to identify noise and also doing the Fourier transform for identifying the frequency shift and this is we're just doing something in parallel now to apply it here to the symbol rate. I believe is something parallel and it could be interesting, but the time frame doesn't fix. It should be something to work on it and to first of all to understand what's happening within your models and your data sets, and then make the devices to do the machine learning and then doing the data analysis and report it. We have to find out what should be given back to the client. I mean, the Earth client should be identified clearly what we want to do with this signal. If it's only for signal processing, it would be fine as well to and there are some algorithm that I know that NASA use for fixing from these deep space probes, fixing bits that they are broken. So the most probable bit is this one. So they put it in and they try to get the noisy signal, bring some signal out of it. So this is the kind of idea. But again, I should have heard your presentation before I open my mouth.
Oh no, I think you're on the right track. The for this particular implementation for the AMSAT UK, it's really kind of going above and beyond to provide any sort of signal identification, but I think we can. Um, the good news is that there's probably only a finite number of signals that are going to appear on the bands, which means that we don't have to have a full blown uh, totally unknown signal sort of system. So if you only have, say, if David comes back and says, just look for these five different types of signals, then what that becomes is a much simpler sort of heuristic design where you're doing the first part of the machine learning where you do feature extraction, which is what you do. Like you say you have a model, you know what your fancy model. When you get a new input, then you do feature extraction and then you go and you run it through the model. So in our case, it might be that we do that feature extraction. We say, like, what's the bandwidth, what's the power, what's the this, what's the modulation index, what's that, blah, blah, blah. And you get that set of statistics. And then you just go do a table lookup and you say it's probably BPSK and it's probably this digital format. So I'm going to guess that that's probably what we're going to do. If we have to do something fancier than that, then we become very power limited because we have half a watt for the whole thing. So the processor, if the STM that we have can run a simple model for machine learning for symbol detection, then we'll do it. But we probably don't need to do like a full blown ground station type of deal. But this will be a really, really good example of using this sort of signal identification. So the first part, that feature extraction, that happens regardless. That's something that all systems would have to do. And we could separate that out and say, okay, here's that implementation in the STM code right here. Like, oh, you want to use a much bigger model that will identify any signal? Great. You're still going to need this this feature set from the unknown signal. Oh, you're going to use the JPL autonomous receiver book from, 2010 or whatever. There you go. You start from the same spot. So at least today, that's what I'm gonna make sure we do, so that we can cover both bases and also reuse this code for like what you're talking about. And I just want to note that like when you say 2 watts, that's actually down over time from like thousands of watts because these systems used to be really intensely power hungry, and they're now down to because of federated learning and because of advancements in machine learning and all of that, the power consumption has come way down. So 2 watts is nothing for a terrestrial consumer. For a LEO, for a 2U LEO spacecraft, it's still too high. But look, 2 watts is really pretty close to half a watt. And who knows, in another couple of years, it might be a quarter watt or a tenth of a watt. So I think, oh, go ahead.
Yeah, you have to think ahead of time also that you're starting in baby steps and you're improving. This is happening to me from last October to now. If you can reprogram your resources during flight, you can increase and maximize the efficiency of the processors and the data analysis because yourself we learn in time what is the priority and what are the models that they have to follow. We don't have a laboratory that we can simulate the whole thing for, I don't know, 6 months, a year, or 2 years. This is an ongoing growing process. So probably upgrade software upgrade should be done. And this is one capability that you have to think that you may have to do to the board. And of course,
Yeah.
you may have a stable hardware, but at the same time, you can improve the efficiency of the data analysis in flight.
Yeah, on orbit upgrades are a big deal. Especially right now with the rapid, iteration that we have. I mean, the things that we're talking about 6 months ago, we would be talking about something different. And as we know, it can be delayed to get your spacecraft into orbit. By the time you're up there, you might have leapfrogged ahead with your design. So not being able to upgrade it is a pain point. I know that AMSAT UK wants it to be upgradable, so I don't know the details yet. I'm hoping to find out definitely maybe before April, but absolutely before June, and then yeah, we'll our this particular design can be updated, yeah, as it goes. There's always risks to this, like if you brick it and you can't get it back, well, too bad. But that's a risk that we take when we send anything into space at all, or even just on a rocket. If something happens on the way up, or even a balloon launch, we've had that happen to us at ORI where balloon launches fail. You know, so
You're reading my mind. I'm sorry to interrupt you.
yeah,
We just added watchdogs into the
yeah, yeah,
software
yep, yep,
that if something doesn't work and within the data set is out of sync for some time, go back to the original software.
yes, yeah. A
Uh,
software watchdog, a hardware watchdog, if you they work together really well. Because you can catch the software reset problem, and then you fall through and you have a hardware watchdog. That's a very classic design.
I don't want to take your time. I
Oh
apologize, but
no,
these are things that you should be
it's
thinking
worth
about
talking
it.
about. Yeah. Yeah. So we'll know a lot more over the next week and what we can do. Basically, what we can do is start doing the sorts of things for MDT that we're doing for Opulent Voice and that Aaron is doing for the CPI and High Faria project. So Aaron's able to show pictures and diagrams and stuff like that and videos of it working, you know, and we have video of Opulent Voice working. And so for MDT, with the hardware and being able to get it all up and running, we'll be able to show a live demo on video. So that we'll be adding that to the mix. So that's really exciting because we're very demo centric here. It doesn't work until it works over the air. And, you can talk about these designs and you can give forum presentations and you can write papers about them, but it's really hard to argue with working hardware. So that's kind of what we're after, is to provide working demos in person, and deliver those designs for free to people that want to use them. So that's kind of what we're doing.
I want to add something else.
Sure.
In space, you have a lot of muons and gamma rays. Even programming or reading memory, it can
Yep.
get screwed up.
Yep.
And you need to have watchdogs, and things get really corrupted by itself, have to be reloaded, praying that the back, the, I mean, this memory bank is clear, so you can recover something back and start all over again and continue working. So even in sounding rockets, we added functions for real value switches, for sensors that they stop working. The watchdog would immediately in 0.1 second continue reading the other ones, and if it comes back, it would read it, but it doesn't stay there waiting for the signal of a sensor or something like that. So you have to be robust. So this is on the spacecraft. Okay, on the ground station it almost doesn't happen. It works like in theory, like the books, but in spacecraft you have a lot of crap that comes from all kind of anomalies.
See you soon, Valerie. Yeah, no, that's true. The Fortunately for Leo, the situation isn't too bad, and there is some radiation. And with some precautions, you're generally okay. The the radiation level is as good as it's going to get in space, but there is some standards, and some things that we fall back on, like the triple redundancy memory. That's what AMSAT UK is baseline, and they have a really good track record here. The Fun Cube is in space and has been in space for a long time. They're pretty conservative with their designs. I don't know if they have any other reprogrammable, like in orbit reprogrammable missions. That's risky because you're opening yourself to corruption during a very critical time. But there's standard ways of doing this. Xilinx has some really good solutions. Yeah, we're using an ICE 40 here, but Lattice Semiconductor has a lot of stuff in space too. So the company is really pretty good about providing, like, here's how you do it. This is the triple redundancy way of doing it. This is so we're just going to use what they recommend. And, um, I'm going to, for us, since we're doing the design itself, if they ask us, then we're just going to point them to, here's the user guide from Lattice about, uh, radiation hardened, or radiation resilient circuits. We're just going to say, oh, you should just use this. And that's what they're already doing. So I think we're in good shape there. But you're exactly right. I mean, there's just been a lot of engineering time spent here to worry about it. For the good news is that since this is destined for Leo, it's high Leo, not low Leo, but it's a high Leo spacecraft. The radiation environment is pretty benign, so it's going to be. I think it's going to be okay. They're doing all the right things as far as I can tell, and if I do get invited to the reviews, I'm sure that we're going to see the usual stuff. And they have a really
What
good.
is the lifetime of the satellite?
That depends on the
Expected
orbit.
lifetime.
It
Yeah, yeah,
depends
yeah.
on
But
Yeah, it depends on the orbit, and they don't know yet. So this is going to be licensed in the UK, and it'll be launched. We're not really sure where, but it'll probably be a UK license. It may be FCC license. We offered to help with that. Um, so we'll see if that, because they don't want low Leo. For the investment, they want it to the orbit to be as high as possible. So we'll see. I don't
but you
know.
have any idea? Weeks, month, 2 years?
Oh,
2 years is very long.
at least a couple of years, at least. So the higher Leo, multiple years is what they're aiming for, but I don't know if they know yet. But not 18 months or anything like that. So significant spacecraft with lots of communication stuff for the community going on. they're going to get as high up in Leo as they can. So might be 5 years. We'll see. We don't know. So hoping to find out. Yeah, good question. Very good question. Let's see if there's anything else. I have a whole pile of notes here. There's some questions that I want to ask them that I scribbled down. Um, because we're designing for 30 kilohertz of spectrum. The 20 kilohertz would actually have been fine, but 30 kilohertz was what Martin Lang originally outlined. So that's what we're doing. And the interfaces look good. The main question is before or after automatic gain control, because that makes a big difference. And that's a question that I don't really know yet. We have our own clock. Um, the 10.7 megahertz is the IF. They have 180 kilohertz full bandwidth for all the other communications functions. So our 30 kilohertz might be anywhere in there. They're just going to have to tell us where they want us to be. I think there's like a KiCad layout for like what the board looks like, but it looks like it's just a 1U, like a typical 1U board. Um, and the questions to them are like, what is there a particular packet format of a signal that you're looking for? Like, when we pick out the signals, should we just try these particular demod decodes first, or should we do the fancier either machine learning or a heuristic, report all the telemetry? How are we reporting the telemetry? Where did the signals go from there? So those are the questions that we don't really have answers yet, that we're relying on the lead to answer. So those questions are going to be now delivered directly to AMSAT UK. And then we have a bunch of tests that we're going to do. Like we're going to simulate and synthesize and test this and bench test it. And then we'll turn it loose on the terrestrial 70 centimeter band and show it working, like just looking around at signals in the terrestrial band. That's what we want to do in April at B-Sides in San Diego, is to have it running and say, hey, this is pretending to be a satellite, and then take it to Friedrichshafen in June. So should be fun. And again, that design is leveraged into our, you know, larger satellite. Our uplink is much wider, so we go from 30 kilohertz to like 10 megahertz, and we go from 70 centimeters to 5 gigahertz. That's a big difference, but it's the same basic design. And it just shows you that the math for multi-rate or polyphase channelizers works for both. If you understand it at 30 kilohertz, 4 channels, you're going to understand it at 96 channels at 5 gigahertz. It's the same stuff, you know. So that's what's going on. All right, any questions about that?
I don't want to sound angry or nothing like that or pushy. What is the timeline? When is the subsystem design review? When is the integrated subsystem design review? When is the full mission simulation?
Yeah, we're going to do everything that for the design as quickly as possible on our end. I haven't been given any schedule other than the launch is going to happen close to October of 2026. So,
Okay, that's quite a good track. So
yes,
these ones are coming very fast as well.
yes. Yeah, this is we're going to hoof it and deliver it as quickly as possible. So, anything that we think they might need, I think we should go ahead and do at this point. Um, Originally, we were providing just the VHDL part, just the FPGA part that does the heavy lifting. I've got you. I'm gonna cut up the spectrum. I'm gonna identify where the peaks are. Here, you do the rest. Well, guess we're going to do the whole thing. So that's our plan, is to just go ahead, deliver that design, finish all of this, and to just start asking the hard questions. Like exactly what the interface looks like. What do you want to do with the results? That sort of thing, and to make it as complete as possible for them. They're going to have to tell us when the meetings are and when the deadlines are. So they'll have to, they'll have
So April 1st is the subsystem presentation, basically.
Well, April 4th.
April 4th.
Yeah,
Yeah,
we're picking that as a
by yourself.
yeah, we're going to already be at the event, and so may as well use that as a public demonstration and to solicit, feedback from people, because there will be some really good signals people at that event. So that's the plan, and yeah, I think we're in good shape. What we've done is kind of keep it simple and straightforward, and this is something that we know how to do, so I think we'll be okay. The the open questions, though, we're going to need answers like really soon. So yeah.
If I were in
You
your
know.
shoes, I would go for the simplest thing that works,
Yes, bingo.
and then from the learning curve, start planning for the next one.
Yeah, I agree strongly. I think that's the way to deliver it, because judging by the communication's been good recently. And the AMSAT UK people are totally busy with this. Like everybody's engaged with like the traditional transponder side. Um, so if we can just kind of like bring up this and
The
reduce the
level, yeah,
risk.
it's a new level
Yeah, if
of
we can make it look like, nope, it does everything that you need, and here's all the test data to reduce the risk, then this will go into the spacecraft. So it's slated, it's scheduled to be there. But we're gonna have to step up and do the things that have not yet been done, that are overdue, to be honest. This is stuff that needed to have already been completed. So if we can close the loop and do it, then we're providing a real service to a international community. So that's kind of the goal.
I'm quiet.
Yeah, it's the usual stuff. Well, I'm sure, Everest, if you have anything that you'd like to share, any questions or comments or reports from the lab, please do.
Yeah, okay. Sorry for mistake of the time.
Oh no, our fault. We're the ones with the messed up time. I'm so
Because
sorry.
because you
Yeah,
changed at 8th of March, and
I know. I
I
know.
didn't notice it.
I'm
Um,
just, I'm very sorry. It's,
no problem.
ugh.
Um, um, on the past week, I work on still on the FPGA for the fishbowl, which is um, a Pluto SDR clone, right? And I work with a friend about. I can maybe show you that. Uh, this is a daughter board for QO100, where there is a GPS and just a power of LNB. And so you can have a GPS DO synchronized. So we have a very good reference clock. And and we have all the, how can you see? I don't know if you can see something here, but you have some F plug directly to the LNB of the satellite, and you have the 13 and 18 voltage, and so it's quite a short cards. And my goal is to implement all that on the Pluto SDR or on this clone, which I call fishbowl. Well, that's it, and I'm quite happy because I have implement I take the one PPS from the GPS and compare it with the 40 megahertz of the VC TSXO, and all done on the FPGA. And then we have now quite a good fix reference crack. Well, that's mainly what I've done on the past week.
Wow, it's beautiful. It is. It's gorgeous. It looks fabulous.
Yeah, yeah.
And this is in okay, so the code is in Tezuka or is it somewhere else?
Yeah. It's on the HDL. Well, it's on Tezuka, yeah.
Okay, cool.
And it is on the Maya. Well, I refactoring the Maya HDL right now in order to have more easy component, which means that we can remove some component. For example, the transmit field, or well, you can add and remove it if you want to do a special case. And as it is by, well, we have some common components, and we have also some specialist tickle for the board, and so it's quite universal. I'm trying to refactoring all that, and I asking me more and more. Well, I am trying to reproduce OpenCPI, maybe, which means that I have to to speak maybe closer with Aaron to maybe to have some common idea, or maybe some I don't know, but this the goal is to have the maximum boards supported with component which could be adding and removing, and I think that it's quite the same as the philosophy of OpenCPI.
Right on. Okay. Yeah, no, and of course you already know Aaron and are able to get in touch with him. And yeah, I think that would be a good fit.
Yeah.
Outstanding. No, and it would look a lovely looking board. That was really nice work. Yeah, so most of our boards do not look that good. So
Mm,
and I don't think that the ones that I'm going to get this week, it'll just be jumper wires. It's not going to be like
yeah, there is a jumper. There is some problem. Well, I have to change the resistor. I have to change some paths with. Well, you have to cut some. Yeah, this is a prototype
yeah.
board.
Well, it looks cool. I am very excited about your work. Thank you so much for sharing.
And I see that you are using now the PM remez for the filter bank.
Yes. Yes, I made that change. Thank you very much for recommending that. That's a big improvement.
When Daniel talk at FOSDEM and talk about polyphase, I already there is some sparkling and say, oh, we have to use it on the filter. Yeah.
Yeah, no, it worked. And it's better. So yes, it's already I closed it out. I think
Yeah.
two
I see that on GitHub. Yeah.
Okay, good. Yeah. And yeah, no, that I think we'll use that from now on. That's a big step forward. So, I'll
Great.
try to spread the word. I'll put it in the newsletter and to let people know about it.
Great.
Yeah, very appreciated. Awesome. Okay. Any other comments or projects or updates? I think Rick, you said you had some news.
Oh, yes. We have been working on our Artemis 2 hardware, software, and systems designs. We made, thank goodness for all the delays in the launch, we have made real progress on our atomic clock, which is not yet in Haswell, but it's here. It's back from repair and upgrades with additional optical filtering that was not available in the original product.
Now, this is the rubidium,
The
right?
rubidium,
That big cabinet of rubidium.
yeah, that's right. I can show some pictures if you want.
Sure.
Let's see. I'll have to go over here and go to here and then share. That's this one, I think. And I go to projects and yeah, where is it? Here it is. And so this is a portion of the command console for the 60-foot dish. And this rack here on the right is our precision time and frequency system. It starts with an HB 5065A. This is not the upgraded modified one. This is my personal one. This one will be swapping them as soon as my foot is well enough to drive. I'll drive down there and swap them out, but they look identical. Below that is a time interval counter, and below that's a GPS receiver. Those are used to monitor the performance and calibrate the rubidium. We do not steer it because we do not want ionospheric and other artifacts of GPS steering, which can throw the frequency off substantially. So we use this for calibration and monitoring of the rubidium. And when we need to, we open up the little panel and turn the knob, but we never change anything during measurement periods. Below that is a 1U 10 megahertz frequency distribution device from Stanford Research. And below that is a shelf with our NTP server and some Ethernet hub and some power supplies and other things. And underneath the shelf here is a computer and a large UPS. The computer is used to collect data every second, 24/7, from both the time interval counter and the GPS receiver. And that data is uploaded here to my lab for analysis every day to be sure that our calibration is as good as it can be, which right now is approximately 1 part in 10 to the minus 12 of on the 10 megahertz, and that's good enough for almost everything we're going to do. Then let's see, I'm going to move this. There's a picture of the entire console, and on the right is the time and frequency station. Just to the left of that, the monitor and keyboard are part of the time and frequency station. Behind the monitor and keyboard are test equipment, spectrum analyzer, which you can't see, and signal generator and other things. In the center with the two consoles is another computer, which is normally the Earth Moon Earth control computer, but it's been repurposed here as the computer that is command and control for all the hardware that's in the feed. All of our primary system is this computer gathering data over a fiber optic link from the feed where the down converter and and SDR and V200 and other items are located. And then this computer does the analysis and data collection. Then to the left of that is a variety of power supplies, and up on top is a backup system, which is does the identical same job as the main system for analyzing data, except it collects its data from a coax cable that is connected to a 3dB splitter at the feed behind the first LNA. And right now, both systems are recording data in real time from a beacon simulating the satellite. And then to the far left is the System 1 dish steering system with the computer down below and the displays in front. And we have three different methods of steering the dish. A manual, a 12-bit encoder system, and a 16-bit encoder system, which is what we'll be using here. And the System 1 folks are working hard on a new upgrade to the software, which will collect data automatically from NASA, from JPL actually, so that we minimize operator interaction while tracking the space vehicle. So that's
Does that reduce the number of people that you need at the site?
no. Almost everything you've seen, I can operate right from here. I don't need to be there, but we always have two people at the site for safety reasons, no matter what. This is Ray and Daryl, who are very proud of themselves because they've just finished installing that entire time and frequency rack and NTP server, which, by the way, has been upgraded remotely by Daryl just the other day, and we're now consistently getting better than 100 microsecond accuracy on standard NTP. And these are just close-ups and a different view of the panel. Outside these windows is the 60-foot dish, so we have a nice view. And these are just close-ups of the various equipment. This is the NTP server.
Oh, cool.
And all of that is accessible remotely using Tailscale and various other. And this is the dish right outside the building. It's 100, or I think about 100 feet outside the building. And that is a recent picture taken by Daryl the same day as we finished the installation. So you can see that when we go down there to do work, it's a long day. We're about to go home, and it's 150 miles home, and the sun is already down.
Yeah, it's a beautiful picture.
Yeah, that is a nice picture. I like that one. So let's see, I can show you if you have a moment.
Sure.
Where is here it is. So I can access that. This. Whoops, what happened? Oh, it's
Never a dull moment.
delayed here on the, nope. Why is it delayed? I want to see the EME.
Computers are such a fad.
I have to say a comment about your antenna. if you allowed me, sir.
Of course.
That is your portable antenna?
Oh, yeah. Yes. Very portable. Um, I'm gonna go back to share. Share what? Share this. Hello. Oh, I don't want to share.
It rolls right up.
Okay. I've got a
Oh, there we
couple
go.
of windows.
Something's happening.
Oops. Oh, good. Thank you.
Caps lock is on. There we go.
Oh, come on. You're great.
This internet crap is a fad.
Okay. Oh, first, there we go.
Yay.
This is the time and frequency computer, and it is, let's see, it is reporting all of this information every second. All of it is being recorded in a data file, and it is telling me exactly what receiver is installed in the GPS. And
Must be Art said helicopter orbiting a few blocks north of us right now.
oh,
Uh-oh.
so um, when I want to gather the data,
Abraxas said, "What up, helicopter?"
Hang on.
oh
There
dear, the time interval counter is reporting this information here, and that information, along with the GPS raw data, is recorded in sets of files. There's 3 files, and every day it rolls over to new files. And then so if you want to know what time it is, that's what time it is. Uh, and so all I have to do to gather the files up is to go here and go down and find out which files are missing and just upload them. I won't do that right now, but I just pick the files that I don't have in my personal computer here and just tell it, bring them here. Then I run the Python code on them, and it tells me it gives me a PDF report telling me exactly what's going on with the rubidium. So I can do all of that from here. And let's see, here's another computer at also at Haswell. This is the EME computer. And well, that's interesting. Huh. The Doppler has been reset. But this is a display of Doppler offset, and it is currently the most expensive thermometer ever made because we don't have the real feed in, nor do we have the Artemis satellite to look at. So we're looking at a beacon located in the control center, and that's showing you the temperature of the control center because the beacon has not got a stable oscillator in it
Right.
on purpose because we
Right.
wanted to see something happen.
Okay, yeah, now your thermometer comment makes a lot of sense.
So here, oh, wait, where did, oh, here we go. Share this. That's closed. Yes, share. Here's an email that came in today. This is the new Mount that we're going to be using for all of our feeds. This is at Roger's house because he's building this mount. And this is our main feed here for Artemis, the 2.2 gigahertz feed. But this mount allows infinite adjustment in X, Y, and Z
Yeah.
over a fairly large area.
Good.
And will replace all of the hardware that's currently in the feed. And this will support all of our feeds from 400 megahertz up.
Oh, good. That's a big deal.
Yes, it is. And of course, we wanted everybody to know how much clearance there is because you see, we have RF connectors and we have cables that have to be attached
Yeah.
and so forth. And there's not a whole lot of room behind the connector if you push the whole package all the way back. So you got an inch and a half to play with, but so now you know what that's about.
Yeah.
And then we have one more. Let's see, that's closed. Now I have to open the drift scan computer. And hello, drift scan computer, there you are. So I have to share the drift scan computer. This this is the backup system for the Artemis. This is instead of running with all the hardware located at the feed, this is with the hardware down in the control room and running a B210 feeding a Raspberry Pi 5 with a 1 terabyte hat. So it's got plenty of room to record data. It's the very same software you saw on the bigger computer running the fiber optic link to the hardware upstairs. And it's recording exactly the same data, except I haven't reset it um, in quite a while. So what you can see here on the left is the temperature variations day and night
Yeah.
for a variety of days inside. And then all of a sudden, here on the right end of it, the temperature goes way down. Or I'm sorry, actually, the temperature goes way up, the oscillator goes down, and then it sort of returns where it was. What happened here is that we had a school group come yesterday and they turned on all the heat in the building, so the
Right.
building was 72 degrees instead of going up and down with the weather. Uh,
Cool.
and
Yeah, you
then
can
we
totally
turned
see
the
it.
heat off, and it returned to where it was. But you'll notice the overall trend uh, showing that it's getting warmer in Colorado,
Yep. Which it is.
which it is, especially 150 miles east of Colorado Springs.
Yeah.
So there you go.
Wow.
So that
Physics works.
and that's and all of that is just what I'm doing. We have other teams working equally hard on various aspects, and everything we're doing for Artemis applies to everything else we're doing because we're learning more about where exactly the feed should be. We've got a much better mounting system so we can more precisely adjust our feeds. We have more fiber optic lines and other things uh, that support our project. So it's
Yeah.
all good, no matter what happens to Artemis.
Very good. Yeah,
Yeah,
no, that's kind of the best way to do it is to try to figure out things that are holistic, where, does it help you either way? It's probably a good bet.
yeah, our software development is
Yep.
maturing. The just there's just so many good things going on.
Oh, it's very good news. Right on. All right. Any
Actually, we'll
questions
take the
for?
Optimus voice over this and bounce it off the moon if we have to.
Sure. No, we're pretty much ready. We have two different modems now, and possibly more on the way. And I don't know if Paul has any comments about the. I think he showed last week the filter curves and everything. We haven't tried to get anything on the air yet. But if you got a B210, if that's what you're using for transmit, then you're in good shape. You know.
Yeah, we have three of them now.
Yeah.
Two
That.
are clones and one is a real one.
Yeah. No, I think we can probably arrange it. So anytime you're willing to give it a shot, we've got got a modem.
Well,
Modem for you.
they were gonna put the drift scan feed back in, and I told them no. Right now, I want to concentrate on Artemis because it
Yeah.
could sneak up on us.
Yes. No, that's true. You should that's a good that's a good strategy.
Yeah, and of course, knowing NASA, uh, we could be.
No,
The problem right
no,
now is
no, because the minute that you change it, the minute that you change your hardware, then we're going to launch tomorrow. That's
we have another deadline coming up, um, and that is Earth, Venus, Earth phase two.
yeah, in October though.
What do you mean? No, October is right around the corner.
That's right, but October. For NASA, that's forever. No, no, you just stick
I'm
with.
worried that NASA
I
will
know.
try to launch in October.
I know. You know it.
How it would work.
Wouldn't that be the thing?
Yeah.
Yeah, so for Earth, Venus, Earth, for Eve, it needs to be a really long transmission. Are you intending to kind of be the transmitting station, maybe?
Oh, of course.
Okay, so you want to be a transmitting station. That would.
So we have, first of all, we're going to move up to 2.4 gigahertz
Mhm.
because the reflectivity of
Yes,
Venus,
that's a better
and
frequency.
we get a half a degree beam width instead of 1 degree.
That's right.
So that increases our power significantly
Good.
and
How long can you transmit?
indefinitely.
Okay. And can you start like a week ahead of time?
Yeah.
Yeah, I
Uh,
think that's
we
going
have
to
a
be
real
good.
problem because I don't think our people realize I just sent out a preliminary, uh, we're gonna ask for some more money. So I've written a proposal like I did for EVE 25. And I'm halfway through it and I just finished the section on where is Venus actually going to be? And the bad news is in October, it will be much closer to the sun than it was in 2025.
For us, yes.
So that if you go plus or minus 10 days, you are still too close. Venus over 20-day period is too close to the sun for optical viewing under any circumstances. That is, at most, at the plus or minus 10 day, we're only 8 degrees off the sun. And it's 6 degrees at the closest point. And most of that period is 6 degrees or 6.5. That is really tight because we found out recently, we accidentally pointed the dish at the sun and we melted some stuff at the feed.
Okay. But
So
you should
it,
be with 6 degrees. You should not. If you're accurate with your pointing, you should be okay.
we should be okay, but we have to be very careful
Yes.
with what we're doing.
Okay. So if you're able to transmit, as long as as Venus is up, if you're able to transmit a signal, you know, um, substantially beforehand, all the way through, closest approach, and afterwards, that's at least a 2 or 3 week commitment. Do you think you guys
Yes,
can do it?
yes,
Okay.
if we can. And the we're planning on, we cannot buy a 2,000 watt or 1,500 watt amplifier, unfortunately. So we're going to probably be using like 4 or 6 200 or 250 watt amplifiers. And that's a commitment of both money and design to get those up there and working. Uh, Last time, everyone who tries this has burned up their amplifiers or burned up their preamps
Yeah.
because the amplifiers fed into them, even though we tried to avoid that.
Yeah, that's
So
why that's why I'm asking, like, would you be willing to be the transmitting station and then
oh,
and not try to receive? Like
yeah,
separate it.
we're gonna do both.
Okay, because that opens you up to the problem of the burning up your preamp. So I'm asking, like, would you be willing to be the transmitting station and other stations be willing to receive?
Uh, I don't think that's our intention. No, we're planning on building a better system that will not burn up the receiver. But yes, we're more than happy to cooperate with the various European stations again. Last time it didn't work out because their license forced them to the opposite end of the band than where we were transmitting, so we couldn't hear each other. This time, that problem won't exist. I'm not sure what limitations they will have if they decide to transmit. Last time they had severe limitations legal, regulatory wise.
Yeah, they
For
got
the
a waiver for the power that they were able to
one
use.
station, not a waiver.
Yeah.
Yeah,
Actually,
and
I
the
think
waiver was only a thousand.
three or four got a waiver, but only one used it.
Yeah, and it was still limited to 1,000 watts,
Yeah.
and we're gonna go with the full 1,500.
Fortunately, the regulator was actually there and saw the whole thing and was
So,
very, very impressed. So I think the next time around it might go a lot better.
yeah, I'm not sure because 2,400 is awfully close to Wi-Fi, and Europe has gotten very sensitive over that.
True,
So
but
it may be harder.
this points up, so they understand about directionality.
Oh, do they?
They
Okay.
do. So
Oh,
the odds are good. So
yeah,
we'll see. But what I'm trying to do is reduce the risk to make it possible for this to happen.
yeah.
So,
Well, if
that's
we
what I'm
have to
after.
transmit longer than the round trip delay, then it'll be a one-way transmission to somebody else who's listening.
Yes. And for the integration times are very long.
I know.
Uh, you know, very long. Like, so the previous like a minute or 4 minutes is not going to cut it. Um, so that means like somebody's going to have to transmit continuously for a long time in order to get a signal, and someone else is going to have to dedicate to the receiver to make it really low risk.
I'm
To
hoping that we can do that so that we transmit long enough to make it work and then they do. So we have a two-way contact with information.
Yes,
So we can declare something new that has never been done before. The
correct,
information could be as simple as the call sign in the station.
correct. That's really you're going to get very few bits through. It's a really low bit rate channel, but the what we've learned, from the link budget and from the link analysis is that this is going to take a, a reliable station transmitting a long time and then swapping. So it's not 4 minutes on, 4 minutes off. It's going to be much longer than that. So, but
Yeah.
it's all in the link analysis. It's all in the paper. You can play around with the numbers and
It's a
see. So if
paper,
you
but
have a
no,
thousand watts, or you have 1,500, or if you have 500, or if you have 1,700, I I mean, going back to what AMSAT DL did, why not get a traditional big whopping, TWT or something old, some sort of big amp that seems like, I mean, they got a huge amount of power.
Well,
That seems like that you'd be able to get something like that instead
oh,
of,
we could, but that requires a variance from the FCC, and we're trying not to do that.
you don't want to ask for a variance.
No, we'd rather not.
That'd make it a lot easier. This would make a lot of things better, because then you'd be able, everybody would be able to reduce the integration time.
Well, that's true. Uh, if we can't do it, uh, then Venus is not going anywhere.
It's
We
going
could
around and
do-
around.
Yeah, we could do this again with higher power, but if we could do it within the regulations, showing that this is possible with regular ham radio equipment that anybody has access to. All they need is a dish, some power, and some good software, and you're off and running.
That's true. But the regulations are designed for terrestrial. So this is just kind of outside of what they were designed to address.
Well, we
I mean, in other words, it's kind of an arbitrary thing to try to
this is
comply
kind
with.
of terrestrial. The sun doesn't come up very high when Venus is there.
Right.
Uh,
But still, like 1,000 watts is not, when you're talking about interstellar sort of comms, that's, in other words, like if there's a way to take advantage of more power, I think you should.
oh, well, there is a couple of ways. There's uh, uh, instead of part 97, there's part 5, is it?
Yeah,
And part 5 is routinely allowed in the ham bands.
true. I think it's cooler to do it as a ham emission, but if you have to get a variance in order to make the link budget work for normal people, otherwise you're talking about literally like days of days of transmission versus hours. I mean, that's a big difference.
It is. It is.
It's sort of
So
like it's like 3D printing. If you have a 3D print and you're going to run your 3D printer, okay, you have a model that's going to take you 40 hours to print. The
yes,
odds of that model failing are actually pretty high. If you print that 40-hour model and you divide it up into 8 sections, each of those, 5-hour prints or whatever, well, that reduces your potential failure rate tremendously. And then you just glue those 5 sections together. And link budgets like this work similar way. If you have to maintain your transmitter for 40 hours versus 5, then I would pick the 5. So it's just a choice on what you all want to invest in and what you
well,
want, what you can maintain in terms of a transmission.
when we first looked at it, we said, well, we'll go even higher in frequency and get more gain. But then we looked at the reflectivity of Venus and it started falling off like a stone. So
Yeah, that's in the analysis. That the 2400 or so is a real good sweet spot.
I think that's going to be what we try. And interestingly enough, we'll be able to use this hardware for some really good moon boats.
That's right. Cool. Okay. Well, I'll go back and I'll see if we can round up some folks and look at the numbers again and we still have the file, so there's still it's all ready to go. I think the
Yeah,
Zeta
has the
2
file
looked
been
really, really
updated
good.
yet to 2400?
Yeah. That's it's
That's
just a number in the spreadsheet. I think that's the default for the current version.
Yeah,
But I
I
think
was
it's
gonna
like the
tell
Zeta
you.
2 looked like it was the best solution. Um, maybe there's another, I don't know. There's a couple of different things a couple of different encodings that are close, but the Zadov Chu is still the best. And, you're just basically transmitting something for a long time and then you get a couple of bits out. That's it, which to most people doesn't sound very exciting, but to us is extremely exciting. This is very, very cool and has not been done before. So anything that can help it become
Even if we only get
reliable, it's
a
good.
couple of bits, we'll be thrilled.
Yeah, absolutely.
Actually, at the moment, would be thrilled just to get a carrier.
Yeah, that's true. That would be a win in and of itself. So I think that's achievable.
One hopes.
Yeah,
Let's see. We're very excited about that, but of course, we've been so focused on Artemis,
yeah,
but everything we learn on Artemis applies here.
that's
Uh,
right.
and oh, by the way, Artemis is 2.2
Mhm.
gigahertz, so we're really learning a lot.
That's
It's
right.
not that different. It's a different feed, but it's not that different.
Very good.
Okay.
Any last comments or questions from anybody before we close up? Well, thank you, everybody. Fantastic to meet and talk, and
Well, I'd like to tell Paul something after recording.
Oh, do you want me
Paul,
to? Would you like it?
yeah, you can turn it off.
Okay.
It's
All right, everybody. See you next week.